Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we will see hands-on kinetic simulations. Okay, this is the example we are going to see. Homogenization problem. We'll see the details for the simulation with an example and then use the software, thermocam software. I'll show the interface for diffusion simulation and how to set up this particular calculation and run it. Okay, when we say homogenization, this is what we essentially mean: concentration gradient becoming uniform. Industrially, removal of segregation is a very important process, which is invariable part of anything that is made through casting, solidification route. And this segregation removal is a very important task before moving to any further processing of the material. For example, in the steel making industries, the steel is made into long billets or ingots which have huge dimensions, and the entire things are put into furnaces where it will be homogenized. And after homogenization, it is taken for any other processing, let's say sheet metal making or bars making, things like that. So all those processing will follow only after homogenization. Otherwise, the processing will be difficult. The material will deform in a very ununiform way. All those problems will come. So it is important to do the homogenization. Therefore, how much time it takes is an important question to ask. This is directly related to productivity. Then we will see an example of iron nickel alloy with a strong segregation. For the example purpose, we will take a slightly exaggerated version of segregation. Let's see that. Okay, this is the iron nickel phase diagram for iron nickel alloy. So this is the material, and this is the concentration profile superimposed on that, and this is how the concentration gradient is: very low nickel to high nickel, and nickel content varies like this in a straight line manner. This is the initial concentration profile. Now, if it is heat treated at certain temperature, the concentration profile changes like this with respect to time. The yellow one first, the orange one second, and eventually this red one, where uniform composition is achieved everywhere. Okay, these are more details. Let's have concentration profile which has segregation of 0 to 50 atomic percent nickel over 0.2 mm. So that's the distance. So in a short distance, that is a very significant concentration gradient, and it's a straight line. This is our initial concentration profile, and the phase is going to be an FCC phase or austenite. We will give this name in the simulation. We will select FCC phase in that name. Okay, we have to create something called the region, and in the region what kind of phases we are going to put, that we can decide. So we will decide the FCC phase with the name austenite, and isothermal homogenization treatment is going to be done, and the temperature for this treatment is going to be 1473 Kelvin. How much time will it take for it to homogenize? In simulation, we will not directly ask this question. We will do simulation for different times. Okay, 3 hours, 30 hours, 300 hours. Okay, we have set up this initial concentration profile, and we tell that this entire thing is in FCC structure, and in FCC, if this concentration profile exists in FeNi system, what would be the time taken for it to become homogenized? That's going to be the question. Okay, I show the phase diagram again to you. You see 1473 somewhere here, and at that temperature from left to right, it is all single phase FCC. Okay, I am labeling only that phase here. So it is all single phase FCC. Since in FCC we have this composition variation all the way from 0 nickel somewhere in this left extreme here, and up to 50 nickel to the middle of the diagram. You can see if you have this much variation in concentration of nickel, it's eventually going to become uniform, and this diagram permits it because it's all FCC, right? So if in FCC we have this variation in composition, eventually somewhere near the middle is where they should converge, and that should be the overall composition of the alloy also. So it will still be FCC and get homogenized. No phase transformations. That is the important thing. In the next class, we will be seeing an example where phase transformation occurs, one phase forming and growing inside another phase, not just homogenization. Okay, let's see how to do that in the software. Okay, so I'm opening this diffusion demo here in Thermocalc software configuration window. This template we are going to use diffusion demo. Previous name was DICTRA, DICTRA, diffusion control transformations, abbreviated in certain way. That was the previous name. Now it is called as diffusion demo or diffusion module in the licensed version. So you can click on this. Right, and here we have to select two databases. So the package here, so click the drop down, select demo steel and FE alloys, FE demo comma MFE demo. Okay. So select two databases. Okay, you can see here databases both are appearing. Okay, FE demo and MFE demo. The FE demo database is something that we have already used for thermodynamic calculations. MFE demo is the mobility database. You can see FE alloys mobility demo database version 2.2. Both these are important. Many times I have seen when I give the training in thermocalc, people make this mistake of not selecting both these databases. They skip this part, select only FE demo and proceed. That's a problem. Thermodynamic database is not good enough. You have to choose mobility database as well. Right. Then in the periodic table you can select the elements Fe, Ni. I'm clicking Fe first, then Ni, because I'm going to change Ni content. Fe will be dependent. Okay. Right. So here our job is done. We can go to second stage. This is diffusion calculator. I'm clicking on that. Okay. Diffusion calculator, and here we have multiple options. We will do one by one. The one in the very top is some basic stuff. Composition unit, mass percent is currently there. Let's change it to mole percent, because we are going to use atomic percent in the question. Since these are only elements, we can use mole percent, and length is going to be 0.2 mm if you remember the question. So we are going to change it to millimeter. Length unit is going to be millimeter, and geometry is going to be planar. Okay, and we have these other options, spherical and cylindrical. We will not use them right now. So depending on the geometry of the problem, you can select these things. For our geometry, planar is fine. I'm clicking planar. Then there are these options. Region 1, we can select create multiple regions for this diffusion setup. In this particular example, we are going to use only one region. So this region 1 will have this FCC phase inside. That's what we should set up. Other options we need not bother much, but I will just read them out and tell what are they briefly. Left interface boundary is where we can select some elements here. So if I click this show left interface boundary, it is asking these questions. Allow phase to form. So if we want certain phase to form in left interface boundary or right interface boundary, we can allow that to happen. If that phase has enough driving force, it will nucleate. For example, in this particular FENI case, we don't have any phase being stable, only FCC is stable. But if at all, initially we have FCC, but that is a two-phase region in the phase diagram, let's say, instead of single-phase region. Then that single phase that we start with will eventually transform to two phases. So the second phase will have driving force to form, to nucleate. So in such cases, we can use this option and do that. In the next class, we will try something like that. Okay. So I'm hiding it back. Then this region part is coming, where this plus symbol is given and region 1 is written. Okay. So this region 1 name, we can change it to austenite. Okay. Name austenite. Then width 0.0 is there, we will put 0.2. Okay, 0.2 mm and 50 points in linear type. Okay. This is okay for us. Okay, what are these options? This 50 points and linear type is 50 different points in this 0.2 mm will be selected, where this concentration profile will be analyzed. But these 50 intervals are chosen uniformly, that is linear type of distribution of points. There are other options. If I click here, you can see geometric, double geometric. What they will do is, they will make the points focused on certain region. For example, if a new phase forms and grows, At the interface, we will have a lot of diffusion activity and the profiles will change drastically there. So that is where we should focus more points of calculation. So this option is for that. We will use that in the next class again. Here we will leave it in the linear time. Then there is this phase name. Click on this none and change it to FCCA1. This knowledge we already have from the phase diagram. If you want to simulate a phase diagram and see, you can directly create a tree and do the phase diagram calculation. I have already shown you the phase diagram, so I am not doing that. So FCCA1 is the phase in which this is going to happen, we know that. So I am selecting FCCA1 directly. Then composition profiles given by function, table input. Two options are there. We can use this given by function option, because if we don't have concentration profile in the table form right now, but we have this linear function going from 0 to 50, we know that. So that's what we are going to set. The dependent component is going to be iron, yes, and component that is going to be independent is nickel, so that is written as component nickel, and the linear type is the function type. So if I keep my cursor there, you can see this pop up: linear, step and function. Three different types we can enter. A linear profile is what is there in this current machine. Step profile is something that you can imagine, we have seen it in multiple places till now, where we have two different compositions and a step profile kind of thing comes. Let's say copper and nickel are joined. This side copper is full and the other side copper is zero. That is the initial profile. So there's 100 copper, 0 copper. So that is a step profile. And any special function also can be used. If you see linear, step and function, all three options come. Step, if you go for a function, you can enter a customized function. Enter a function in the field. Any valid expression that is a function of a distance variable x will work. For example, a sine curve 10 plus sine x square. Okay, that can be used. Some useful functions are error function and Heaviside step functions. They all can be set up. Okay, so we have set up this linear now. Then we can give what are the values here, from what to what. That is in linear form. It will go from 0 to 50. 0 here, 50 here. The moment we enter this, in the right side visualization window, you can see a composition profile tab appearing with this picture, where mole percent 0 to 50, nickel is going from 0 to 50 like this, over this 0.2 mm. Okay, so that is given here. Okay, 0.000 to 0.200 in mm. This is the composition profile. So we have set it up. Okay, and then the right interface boundary, again we are not going to bother about that. We are not going to set up any phase there. And after that comes left boundary condition and right boundary condition. So what are boundary conditions? This is different from setting up any phase to form. This is more important. If you remember the carbonization example, where we said that from the surface there is a continuous carbon supply and concentration of carbon in the surface is Cs value, which is constant. So it's not that you say you supply some carbon and immediately as the diffusion starts, carbon content will go down in the surface. That is not so. Continuously carbon content will be maintained. So that is a boundary condition we said. That can be set up here. You can see left boundary condition, right boundary condition, both can be set up. Right now it is closed system. This is okay for this particular example, where we just want homogenization to happen within the sample and nothing is going to come from outside. So here in this boundary condition, if you see, mixed zero flux and activity or composition. So if any element is having some flux or activity at the surface, we can set it up, or certain composition also we can force for certain element at the surface. So this is possible. In this example, we will not take that. Okay. Then thermal profile, isothermal heat treatment is what we are going to do. So in isothermal, we are going to set the temperature. We said it is going to be 1473 Kelvin. So type 1473 Kelvin. Then simulation time. Here seconds, minutes, hours, days are there. I am selecting hours here. So in simulation time, let's keep 30 hours as our first option. Okay. So if I enter all these data here, then you can see diffusion calculator is not showing any exclamation marks or alert signal. Okay. Otherwise, there will be a yellow circle within which you will have a alert symbol, exclamation mark will be there. If that is present, it means some of these conditions are not entered the setup is not complete. So you have to check which are the data to be entered, then you can see that this thing is now vanished, no symbol is there. If I remove this condition, if you put 0 here, simulation time 0 here, you can see this exclamation mark here. Okay, so only when all the necessary conditions are entered, you will see this exclamation mark or this alert symbol vanishing. Okay, now I am going to enter 30 here. Now you see it's not there, so the setup is complete. Okay, so now we are good to go for the calculation. I'm clicking perform tree. Right, okay, so we can click on this plot renderer here and be able to see this. You can see distance 0 to 0.0002 meter. So the diagram comes by default in meter. Mass percent is not from 0 to 50, it is just above 5 to just below 40. This is what has happened after 30 hours. It has not become flat. Okay, so if you want to change the units and visualization a bit, you can do that here. Composition of nickel in mass percent is coming. Let's change it to mole percent, because we have set up 0 to 15 mole percent. So let us change it here, and then in the hours 30 is written here. Let us bring the 0 hour data also here. So at the initial 0, give a space or comma, anything is fine. 0 space 30, both I am putting here. Then unit of x-axis, I want it in millimeter, that's all. Then click perform again. Okay, now we see picture with 0 to 50, the initial profile, the blue one is here, and then after certain time, 30 hours, it has become like this. 30 hours seems to be not enough for the homogenization to complete. Okay, let's keep it like this. You click on diffusion calculator again. You see this pause button, pause play button here. So that can be pressed only after changing the time here. Okay, simulation time is the only thing you can change in the setup. If you see this left and right boundary conditions can be changed, or simulation time can be changed. These are the options which are possible after running a cycle of diffusion. Okay, so now simulation time is going to be 300 hours. I'm going to click continue now. Okay, so calculation is complete. Let's go to plot renderer. Okay, here 0 and 30 are plotted. 300 has not yet come, so we have to type 300 here. Give a space and type 300. Then click perform. Okay, so 300 seems to be enough. More or less, it is near the middle. It's almost flat. So we can say 300 hours are good enough for the homogenization to be achieved. Since it's only a simulation, let us run it for 3000 hours also and see what happens. Okay, so I'm going to type 3000 here and continue. Okay, it's done. So I'm going to plot renderer, typing 3000 also next to it. Click perform. Okay, it is definitely flat. Okay, possibly 3000 is more than enough. If you are using 3000, you are possibly wasting the furnace time. Okay, so this is definitely flat after 3000 hours. Time is displayed here. 0, all these things are in seconds. This is 30 hours, 300 hours and 3000 hours. Okay, okay, you can imagine how useful this is. So if you want to do actual trial and error to optimize this homogenization heat treatment time, how much of effort should be there, how much of material and manpower should be wasted. Here you can see this can be so beautifully simulated. Even up to 3000 hours, within matter of minutes we have completed it. So this is the usefulness of diffusion simulation. We will see phase transformation simulation in the next class. That will be even more interesting. Okay. Thank you. I hope the lecture is useful. See you in the next class.